Hello everyone. A very warm welcome to the University of Bedfordshire and to this public lecture, an evening or perhaps more accurately a late afternoon with Dame Jocelyn Bell Burnell. My name is Rebecca Bunting and I'm the Vice-Chancellor of the University. I'm delighted to welcome you all. At last count we had over 470 requests to attend this event, which is both a testimony to Dame Jocelyn and her work and a record breaker for the university. There will be an opportunity for questions after the presentation, which I hope you'll join in. And may I encourage you to use the Slido app located to the right of the screen to send in your questions, and then I'll put them to Dame Jocelyn. It is my pleasure to welcome and introduce our speaker, Dame Jocelyn Bell Burnell. Dame Jocelyn is an astrophysicist. Her discovery of pulsars in 1967 as a postgraduate student at the University of Cambridge is described by the Royal Society, a fellowship of hundreds of the world's most eminent scientists, as one of the greatest astronomical discoveries of the 20th century. Dame Jocelyn has been a member of the Royal Society since 2003. She worked for several years at the Royal Observatory in Edinburgh and has worked in a number of universities throughout her career, including Southampton, UCL, Bath and the Open University. In 2018, Dame Jocelyn was installed as Chancellor of the University of Dundee. She is currently a visiting professor of astrophysics at the University of Oxford and a Fellow of Mansfield College. She has held roles as President of the Royal Astronomical Society and President of the Institute of Physics. She has received numerous recognitions, prizes and awards throughout her distinguished career, and in 1999 was appointed Commander of the Order of the British Empire for services to astronomy, and then in 2007 Dame Commander of the Order of the British Empire. Dame Jocelyn's championing of science and women in science has been inspirational and pioneering. In 2018, when she was awarded the Special Breakthrough Prize in Fundamental Physics, a prize of £2.3 million, Dame Jocelyn chose to use the prize to create a scholarship fund to support female, minority and refugee students seeking to become physics researchers, a wonderful legacy of her work. I'm delighted that Dame Jocelyn has been able to join us today, a most fitting end to a month in which the university has celebrated International Women's Day and our Festival of Science. I'm sure you will all give a lovely virtual round of applause to welcome Dame Jocelyn Bell Burnell to talk to us about how we are all made of star stuff.
Thank you, Vice-Chancellor. And thank you everybody for joining in this evening. We are made of star stuff, literally, and I will explain how. Could we have the next slide, please? So I'm going to talk a bit about some of the chemical elements that we find in our bodies. Then I'm going to go right back to the beginning of the universe, talk about the Big Bang. That is its official name. How the stars create some of the elements, about star death by explosion and how that creates more, and how stars, planets and people came to be. Next slide, please. So I'm going to start by saying a little bit about the chemical elements. Next slide, please. Starting with some student answers to exam questions. You don't really need to know the exam question, but one answer said H2O is hot water and CO2 is cold water. If we were in a live audience, I would now ask you do you think that's correct? And I expect I'd see a lot of heads being shaken. It's not correct. H2O is hot or cold water. CO2 is carbon dioxide. Could I have the next slide, please? Here's another student answer. Water is composed of two gins, oxygen and hydrogen. Oxygen is pure gin. Hydrogen is water and gin. You can then start round again because you need to say what water is. To reassure you, these are not British student answers. Next slide, please. There is a website where you can find some of the best answers that students give to questions. Thank you. And the next slide, please. So we've met hydrogen, oxygen, carbon, H, O, and C. There are actually a lot of chemical elements, and you may have seen diagrams a bit like this, maybe hanging up in a chemistry laboratory at school or a science laboratory at college. Hydrogen is top left. Oxygen is in the second row over towards the right, and carbon is nearby it, just a couple to the left. The layout of this table is it starts with the lightest elements, and then the next lightest, and then the next lightest, gradually getting, the next heavier, and the next heavier, gradually getting heavier and heavier. So heavy ones like uranium are down near the bottom. The columns are also important. All the chemical elements in a column have similar chemical properties. So for instance, the lot over on the extreme right, helium, neon, argon, and so on, those are known as the inert elements. Those are elements that don't wish to do anything. They are the please leave me alone chemical elements. Whereas the ones on the extreme left, hydrogen, lithium, sodium, potassium, and so on, are extremely reactive. Maybe you saw demonstrations in a school laboratory of what happens when you put a little pellet of sodium on a basin of water. It goes skidding around very, very fast and then bursts into a flame at the end. And in between these two extreme columns, there's a gradation of how reactive the chemical elements are. I'm going to work with this table. I'm going to be picking out on it the various chemical elements I'm talking about. But so far we've had hydrogen top left, carbon and oxygen in the red row, the first one that's a row rather than a single. And we will go deeper into the periodic table. Could I have the next slide, please? So we're going to be interested in what we are made of and where that stuff came from. So take a moment to think what the main chemical elements might be in your body. And as a big hint, we are 2/3 water. And I think you now know what water is. H2O, hydrogen and oxygen. In our lungs, there is oxygen. What about in the tissues of your body? What do you think might be there? There's a lot of carbon and oxygen and hydrogen. Why is our blood red? What chemical element makes it red? If you're anemic, you maybe have to take iron tablets because it's iron in our blood that makes the blood red. And finally, for this, because I can't do every chemical element, what's in our bones? There's calcium in our bones. Those are the chemical elements that I'm going to track. Next slide, please. So hydrogen, oxygen, carbon, calcium, and iron. Now, there are many other chemical elements that are needed for life. They're usually in smaller amounts, but things like, for instance, potassium and lithium are very important for brain health. So although I'm only going to talk about those top 5, there are others, but if we can understand how we got those 5, you can probably guess how we got the others. Next slide, please. Right, I'm a physicist, an astrophysicist, and physicists take a bit of an overview. So I'm going to discuss our life, taking rather an overview. When we were born, we were a good deal smaller than we are now. Our bodies now contain more atoms than they did when we were born. Where do you think those atoms have come from? How did we gain those atoms? How did we grow? A lot of it is from food and drink. So let's think about the atoms we've gained from food and drink, and wonder where those atoms were before they came to us in food and drink. Well, food, the vegetable stuff, the fruit stuff, grows from the ground. Tiny seeds grow. They must be taking up atoms from the ground, from the air, from the rainfall. And the liquids we consume, well, some of the same and a lot more from the rainfall. So the atoms that are in the ground, where did they come from before they got into the seeds and the plants and into us? Next slide, please. Rather than pushing back from where we are now, having decided that what we need to understand is where the Earth got its atoms from, I'm going to jump us right back to the beginning of the universe and work us forward to the formation of the Earth, and hence us. Next slide, please. So our universe had a distinct beginning. It was about 13.7 billion years ago, 13.7 thousand million years ago. And initially, everything, all of space, all of matter, all of energy, were in a tiny, tiny volume which exploded rapidly. Huge explosion. It was initially nicknamed, in a slightly disparaging way, the Big Bang. But the name has stuck. That is the official name for the creation of our universe. So all of space, all of matter, all of energy came from this huge explosion. And what we call time starts with that explosion. Which means if you want to know what happened before, you're not asking a question that can be answered. In fact, it's not even a proper question, because if time began with the Big Bang, questions about what there was before don't make sense. There's no time, there's no before, or there's no before that we can know from where we are. Next slide, please. So in the microseconds after the Big Bang, we've got a great big fireball of energy. It's very hot and it rapidly expands, and as it expands, it cools. Initially, all is light, truly blinding light, but as this thing expands, some exotic particles begin to form. Einstein's famous equation, E equals mc squared, was working way back then. And some of the energy is turned into M for mass, matter. And that equation, E equals mc squared, tells us how much energy has to be taken up to make how much mass. Next slide, please. A few minutes after the Big Bang, the temperature's a cool 1 billion degrees. It's actually billion degrees Kelvin, but it doesn't much matter what temperature scale you're on. It's big. And there are the nuclei, the cores of atoms of hydrogen, mainly. Tiny amount of helium and some heavy hydrogen like deuterium and tritium, but predominantly hydrogen with a bit of helium. The next slide, please. So going back to our famous colourful periodic table, From soon after the Big Bang, we have hydrogen top left and helium top right, and nothing else. So right back then, we could not have existed because there weren't available the chemical elements that we need. There's only hydrogen and helium, and you cannot make people or animals or plants out of hydrogen or helium. Next slide, please. Scientists can sometimes be a little bit fey. This slide is labelled Goldilocks effect. And the Goldilocks is the Goldilocks and the Three Bears Goldilocks. Really, genuinely. Do you remember the story of Goldilocks and the Three Bears? How Goldilocks visits the Three Bears' house while they were out. And she tries their chairs, and Daddy Bear's chair is too big and Mother Bear's chair is too soft and Baby Bear's chair is just right. And she tries their beds, and there's something similar. Daddy Bear's is too something, Mother Bear is too something else, and Baby Bear's bed is just right. And likewise with their porridge, which was sitting on the table. Baby Bear's porridge is just right. Scientists now label circumstances which are just right for something to happen. They label it a Goldilocks effect. And in the early universe, there was a short interval between 1 second after the Big Bang and 3 minutes after the Big Bang, when conditions were just right for something to happen. And what happened in that 3 minutes or 2 minutes 59 seconds period is that the early universe could form the nuclei, the core of hydrogen and helium atoms. Before 1 second, everything was still too hot and too dense, and everything was rattling around at a high speed and banging into each other. Don't know if you remember dodgems cars, a bit like dodgems. There were frequent collisions, and if anything merged, it frequently got broken up again. After 3 minutes, the early universe has expanded so much, so rapidly, that everything is very much spaced out. And it's also cooling, so it's moving more slowly. And so with a very thinly spaced stuff all moving rather slowly, there's very little chance for particles to meet and make anything bigger. It also means that any hydrogen and helium that is formed is not going to get disrupted, broken up. So between 1 second and 3 minutes after the Big Bang, we get hydrogen, which is one of the things we're looking for. Helium also forms. We don't actually need that in this story. The next slide, please. So of that list of elements that we need for human life, we've got oxygen, we've got hydrogen from the early universe. Thank you. And the next slide, please. The universe continues to expand and cool, and all the particles that there are move further and further apart, and there's no chance of anything else forming directly from the Big Bang. So there could not have been life shortly after the Big Bang. We need more chemical elements, and we need them to join up. So where did all the other elements come from, if not from the Big Bang? Next slide, please. The answer is they were created in stars, particularly in massive stars, big heavy ones. And I'm now going to talk you through the birth, life and death of stars. I did warn you that this is a bit of an overview, this talk, so millions of years going to be crammed into millions of milliseconds. Next slide, please. Gravity at heart is what forms stars. We have lots of primitive particles scattered around the place, a bit like a gas. There might later on be some dust particles as well, but at least there's hydrogen and helium nuclei. And stars form when some of this material gathers. There's a random little knot which has extra gravity. That extra gravity pulls in some more particles into the knot, which puts up the gravity, which pulls in more particles, which puts up the gravity and pulls in more particles. And gradually what was a really fairly inconspicuous knot grows and grows and grows. Next slide, please. This is where we get star formation these days, in some of the dark parts of the galaxy. This is a famous part of nearby galaxy. It's called the Horsehead Nebula in the constellation of Orion. And you can see just center right, a dark shape against a pink background. That dark shape is in the shape of a horse's head. It is not, repeat, not a horse's head. It just happens to be a shape of a horse's head. And so this nebula is called the Horsehead Nebula. In this slide, you can see a number of stars, particularly in the top right. There's a lot of very faint little stars. If you can magnify the image on your screen, you'll be able to see that there are. There are far fewer stars in the bottom left. It's much blacker. The pink-red splodge in the middle is hydrogen. Hydrogen gas, when it's excited, glows red. If any of you have looked at a hydrogen lamp in a physics darkroom, you'll know that it has a red spectral line. This is hydrogen in its red spectral line. And since 90% of the universe is hydrogen, whenever now you see an astronomical photograph with a red splodge in it, you can say, "Ha, hydrogen!" And you'll be right 90% of the time. So lots of hydrogen. Comparing top right with bottom left, many more stars top right than bottom left. That's because in the bottom half of this photograph, there is a dark cloud, a cloud that absorbs the light from stars beyond it. And you only see the relatively few stars that are this side of the cloud. It's in dark clouds like this that stars form these days. There's probably quite a bit going on in the Orion Nebula. And it's in these dark clouds that there might be a random gathering of particles that's slightly denser than surroundings. And that denser thing with its gravity pulls in more particles, which increases its size and puts up its gravity, so it pulls in more particles, which increases its size, etc., etc., etc. As that little random knot grows and grows and grows, it gets hotter and hotter in its center. Could we have the next slide, please? So, top diagram shows this little knot growing. When the temperature in the center reaches about 10 million degrees, and it doesn't matter whether it's absolute or Fahrenheit or centigrade, they're all much the same, but technically it's degrees absolute. When we get 10 million degrees absolute, nuclear fusion reactions can start, nuclear burning. And in fact, what happens first is that 4 hydrogen nuclei get together and make a helium nucleus. This releases some energy, and that energy is what makes the star shine. And it will keep on shining as long as there are hydrogens to combine to make helium and release energy. Next slide, please. So this is what's going on inside the sun at the moment. The left-hand diagram is another version of what I've said. 4 hydrogen, the red dots, merge, combine to make helium, which is the lump of 4 balls just to the right of the arrows. And the sun will continue doing this for about 10 billion years. But there's a finite amount of hydrogen in the sun, so one day it will get short of hydrogen, and that reaction on the left-hand side will diminish and indeed stop. And the core becomes choked with helium. Now, the sun And stars like the Sun have another trick. They can take 3 of these helium nuclei, 3 of these 2 red, 2 blue nuclei, and combine them to make carbon. And that's what you see on the right-hand half of the diagram. And that also will release energy and will enable the Sun to go on shining for a bit more. Not nearly so long, but a bit more. And look, now we have carbon for the first time in the story. And carbon is one of the elements we need for life, although at the moment it's stuck in the centre of a star. Could we have the next slide, please? So if you took a cut through a star like the Sun, you'd see in the centre hydrogen was converting to helium and giving out energy. Sorry, that's a younger version of the Sun. And the next slide, please. The next thing that happens is in the very centre, some of the hydrogen combines to give helium. Outside that, there's the helium. Sorry, I'm making a right mess of this. In the very centre, you have helium converting to give carbon. 3 helium to give a carbon. Outside that, you have 4 hydrogen converting to give helium. And outside that, you have a reservoir of untouched hydrogen. Next slide, please. So of the elements we needed for human life, or the ones I'm talking about, we've got hydrogen and the carbon, but the carbon is locked inside a star, and that's rather hot and not available to us. And the next slide, please. The Sun's life will end at that stage. It will stop generating so much energy. It'll become what we call a red giant star. It will cool a bit and be red rather than orange-yellow, and it will swell enormously. It will swell and engulf the planet Mercury. It'll swell and engulf the planet Venus. Whether it engulfs Earth or not is a bit iffy, but frankly, if the surface of the Sun comes that close to the Earth, I would not recommend staying. But if there are stars that are much more massive than the Sun. The stars in the Pleiades and Betelgeuse, for instance, are much more massive, and they have several more stages, and they will make some of the bigger nuclei. The next slide, please. So I'm going to do this on this periodic table chart, and I don't have a pointer, unfortunately, but I hope you can see that some of the boxes have got black rings around them. So we started with carbon in the first red row. Carbon will convert to neon, end of that row, then jumping over to the left, then sodium and magnesium. And each of these reactions will give out energy and will keep the star shining. It would keep the Sun shining for about 600 years. Next slide, please. After that, the neon converts to oxygen. That will keep the star shining for about 1 year more. The timescale's getting tighter and tighter. Next slide, please. Oxygen can convert to silicon. That stage will last 6 months. The next slide, please. And in 1 day, the silicon will convert to sulfur, and then argon, and then calcium. And then, next slide, please. The calcium will convert to iron and nickel. And here the star has a serious, serious issue. And this includes our Sun, which is one of these stars. Next slide, please. The star looks a bit like this. It's not to scale, I have to say. There's a lot more hydrogen in the outside, but in the centre, there's iron and nickel. Outside that, a layer of silicon, then a layer of oxygen, then neon, then carbon, then helium, and a chunk of hydrogen. Next slide, please. So of the elements we need for human life, we have got all of the ones we were following, but they're locked inside a star. Next slide, please. For the physicists in the students, physics, professional physicists, hydrogen is at the top left side of this diagram. Iron is down the bottom, helium between them, and the heavy elements like uranium is off to the right. You can fuse elements like hydrogen and move down this curve to iron. You can't go any lower than iron, so with fusion you can't get energy out of iron. If we start with the heavy radioactive elements like uranium at the extreme right, you can go down that slope, fusion, and my computer's sending a funny message. Okay, somebody will shriek at me if something's gone wrong. Starting on the right-hand edge, you can fuse nuclei like uranium and get energy out right down to iron. But once you've got to iron, you can't go anywhere. It's uphill. So iron is the pits. Next slide, please. And what happens is the star explodes. And all those layers of material get kicked out into space. Next slide, please. We call these explosions supernovae, Latin for super new star, understood. Supernovae were originally observed by the ancient Chinese, and we observe a lot of them today. They mark the explosive end of a star that had done all this fusion of hydrogen to helium to carbon to iron, and then it exploded. This photograph is of part of a nearby small galaxy called the Large Magellanic Cloud. It's named after Magellan, the explorer, but when you turn Magellan into an adjective, Magellanic, it's hard to recognize the name. And you can see lots of that pink stuff. Remember me saying that's hydrogen? And you can see a glowing mass of stars, gas, up on the top left. If you've got a big screen, you can see zillions of little stars dotted all over the place. And bottom right, one star has an arrow pointing at it. Let me be absolutely clear. The arrow was added after the photograph was taken. There aren't handy arrows in the sky telling you which star to watch. But watch that corner of the photograph. Next slide, please. That tiny little star that needed pointing out with an arrow has exploded. It's become one of these supernovae. It's gone through all the process I was talking about, ending up with an iron core, and then has exploded, distributing a lot of its contents over the nearby universe. So making available hydrogen, helium, sure, calcium, carbon, iron, all sorts of useful chemical elements like that, distributed through space and subsequently gathered up into the next generation of stars. Next slide, please. Now, one of these explosions produces a horrendous amount of material, 400 million tons of carbon, 60 million tons of sulfur, 200 million tons of radioactive nickel. It's the radioactive nickel that keeps the remnant shining, typically for a couple of months. And all this stuff is spewed out into space, distributed through space, ready to be gathered up into the next generation of stars, forming in some of those dark clouds. And the next slide, please. Digression. If a star near to us exploded in a supernova, would it be dangerous? Because along with all these useful chemicals, a supernova gives gives a blast of gamma rays and X-rays. Betelgeuse in Orion is the nearest star most likely to explode sometime. Recently it dimmed a lot and people thought, is it going to explode? Is this some sort of precursor? But it hasn't, and indeed it is largely recovered. Furthermore, it's more than 25 light years away, and we feel therefore it's at a safe distance, even if it does explode. It's only big stars within 25 light years that might be a hazard for the Earth when they exploded. So we can watch Betelgeuse and see what it does in a relatively relaxed manner. Next slide, please. So, how did the elements like oxygen, carbon, calcium, iron get here? We've seen that they're formed in a supernova explosion, and the explosion distributes them widely. What's happened is, a long time ago, there was several supernovae explosions. The material spread out, it got gathered into newly forming stars. You know, in those dark clouds where there were little groupings of particles with extra gravity that pulled in more particles, that put up the gravity and pulled in more particles. Some of those particles that got pulled in will be some of this oxygen, carbon, calcium, iron from the very first exploding stars. And some of those stars that form are also big stars and will in their time explode, having generated further oxygen, carbon, calcium and iron inside themselves. And this doubly enriched oxygen, calcium, carbon, iron, etc. material gets spread out through space. And some of it gets incorporated into new stars. And one of these new stars is called the Sun. The Sun is a third generation star. The material it's made of is enriched by typically 2 previous supernova explosions. So it's got a double dose of oxygen, carbon, calcium, iron, to put it bluntly. The star forms in one of these dark clouds. The particles pull together under their gravity. It gets so hot in the center that nuclear reactions start, hydrogen converts to helium, and light is given out. And that's what's going on in our Sun. Not all of the material got incorporated into the Sun. Some of it was left over and formed a big disk around the young Sun. And the particles went round in this big disk and gradually banged into each other and formed lumps. And lumps bumped into each other and formed bigger lumps. And bigger lumps formed bigger lumps still, and so on, until we ended up with a load of planets and probably also the asteroids. So the Earth is made of material left over from the Sun, and it's made of material that's been through 2 of these supernova explosions. It's third generation material, and it contains enough oxygen, calcium, carbon, iron to allow life to develop on Earth and life like us to form. Could I have the next slide, please? So to summarize, the Big Bang formed some of the chemical elements, just a few. Some of the rest were created inside stars and made available to us through those stars that had an explosive death. I haven't talked about heavier elements, things like gold. They're formed when 2 stars collide. But if it weren't for the stars, we would not be here. We are made of star stuff. We are intimately and ultimately children of the stars. Indeed, in a sense, you could say we are stars. Next slide, please. I finish with this quote from Carl Sandburg, a USA poet. Remember who you are. Remember you are one of the latest products of millions of years of toil and play and regurgitation of universal forces. The rain and stars and dust of 1,000 worlds that have perished have contributed to the making of you. Thank you. Last slide, please. Thank you very much.
Thank you very much, Jocelyn. Well, we've had an enormous number of questions posted, and I'll try and make some sense of them. I'd like to invite you onto the stage to have a nice cup of coffee and relax now, but it's not that easy in this situation, is it? But thank you very much for making complex theory and science so accessible through that presentation. So I've got lots of questions, some of which are really quite technical, so they're going to test my ability to even read some of them, I think. But one early question was about, why do life forms need carbon in particular? Could life be based on a different chemistry, in fact?
I'm not a biologist, but I believe it doesn't have to be carbon, but carbon is actually the best. So it's most likely to be carbon-based. I think silicon is another contender, but carbon is easier to make, there's more of it. So I think it's more likely to be carbon-based.
Okay. And how did the dust form from hydrogen and helium, which are gases? I think that was an early question as well.
It's a grouping together of the nuclei of some of these elements. Hydrogen and carbon frequently combine to make dust particles. Sometimes they attach oxygen, sometimes they attach calcium, sometimes other things, but it's primarily hydrogen, carbon, bit of oxygen, bit of calcium.
So we've obviously got some very knowledgeable people in the audience who are sending in some very technical questions. I'll come on to some more general ones in a moment about your career and about the education of science, but just to keep going on one or two of these rather technical questions. Simple amino acids have been detected in interstellar clouds and on comets and meteorites in space. How soon after the Big Bang did these first compounds form?
I don't know the answer to that, but I think it's probably quite late, to be honest. And you'd have to be fairly choosy about where they formed, because they could be fairly easily broken up by starlight or X-rays from young stars, for instance.
There's a rather whimsical question that came in first, Dame Jocelyn, which was about how much time have we got before we all return to being stardust. I don't know whether you have any views on that.
The sun is steadily evolving, and I described how it would expand, swell, and whether it engulfs the Earth or not is a moot point. But certainly we'll have to be gone somewhere else if there still are people around. Ultimately, the sun and other stars will run out of energy. They will go black. This is after their swelling phase. They will go black. Black holes will have a field day. They will gobble anything that comes too close. But apart from black holes, in that phase of the universe, there's not a lot of activity, shall we say, and there's certainly not a lot of light. I think the ultimate fate of the universe is a number of black holes gradually moving further apart, and no signs of life anywhere.
So, right, it's a rather depressing thought, isn't it? A question about light travelling from our star, and I'm reliably informed by Anonymous that it takes 8 minutes to reach us from its creation inside the star, but sorry, it takes 8 minutes to reach us, but from its creation inside the star, it's taken much longer to travel outwards, as you explained. Could you explain that a little bit more?
Yeah, if you get light generated well inside a star, the star is very dense and the light has to fight its way out, and it fights its way out by bouncing off particles. So it's got a very, very, very zigzag journey and takes a very long time to escape, and has many, many bounces, many collisions on the way out. Once it gets out, it's easy. It just can go freely.
And how do we know that the sun has been through 2 supernova explosions? What's the evidence for that?
The sun itself has not been through 2 supernovae. It's the product of the debris from 2 supernovae. And we know that by studying the amount of, for instance, iron in the sun, which we study that by looking carefully at the light that comes out of the sun. And we can see the chemical composition of the sun by looking at its spectrum.
And a question that I had at the start and has just come in as well is about that, the question that we all want the answer to. What triggered the Big Bang? And what was there before the Big Bang? Do you have any insights you can give on that?
Because time, what we call time, what we know of as time, began with the Big Bang, before the Big Bang is a non-sense question. I won't say that faster, it might be impolite.
Yes.
It's not an allowable question, I'm afraid, Vice-Chancellor.
I understand.
Giving some of your staff some ideas, but it's not an allowable question.
I understand. And have we observed a first-generation star, and are there any left today?
I'm not sure there are any left today. I'm not absolutely sure about that, but we have reasonable understanding of what they were like, but not much chance to check that our understanding is correct. It does at least give a different story.
Just moving into slightly wider areas, has knowledge from older civilizations, or even modern day citizen science, which we know is a very big movement now, has it contributed to development in this area, in your area of expertise and our understandings of astrophysics?
Yes, there's one particularly famous example. In 1054 AD, the ancient Chinese observed an exploding star, a supernova, in the sky and recorded it. And we now know that that exploding star is created what we call the Crab Nebula, a very famous astronomical object in the northern sky. So that helps us date it very exactly to 1054 AD. There are probably other ones as well, but that is the best example from the ancient Chinese records. And those are probably the best documented records. There are some early North American hieroglyphs, not the right word, glyphs maybe they're called, paintings on rocks, symbols on rocks, which some people interpret as being exploding stars, which could be so bright that they could be seen without a telescope. But certainly the Chinese records are the best example I know.
And do you think that citizen science has a place in serious science?
Yes, citizen science is hugely important. Astronomers have so much data, they can't do it all themselves. Having intelligent people look at the data, see things that we might have overlooked, see things that we wouldn't have thought to program the computer to look for example. There was a lovely example which was known as green peas. An early astronomical project asked members of the public to help look at galaxies and say whether they were spiral or not spiral or whatever, classify them. And a woman in the Netherlands was looking at these images and came back to us and said, some of these photographs are things that look like little green peas in the background. What are they? And we'd all been so focused on the galaxies that were the subject of the survey, we hadn't noticed these green peas. And it turned out that they are more distant galaxies with a lot of oxygen. Oxygen shines in the green. The northern lights, for instance, it's the oxygen that's shining green. And so, because a member of the public was looking rather more widely than the overworked, focused scientists, she spotted these green peas and drew them to our attention, and they've become a new topic of research.
Fantastic. Just what we need. And it relates also, doesn't it, to building that interest in young people and young children as well. And there are a number of questions about how we educate children to understand the kinds of work that you're doing and how important it is, and that they aspire to careers in astrophysics and other science areas as well. We know that's a big challenge in the UK, particularly, to get children really engaged in science. Have you come across any really good examples of how that's worked in your work to really build that sense of awe and wonder, but also aspiration to do this work in young people?
I think there's a lot going on. I don't have particular expertise in the area, but I'm aware of quite a lot of publications and websites and things promoting astronomy, talking about the universe, talking about being an astronomer. I think there's quite a bit around.
Yes, I think that's right. It's very much something that schools and colleges are very keen to develop, because it's about engagement with life, engagement with things that are happening around them, and keeping children kind of engaged and in awe and wonder at these things is quite a challenge, but very, very important. There are a lot of questions about why we haven't found life elsewhere. In summary, as a question, what do you think there will be? What do you think about Mars?
Probably not as near as Mars, probably much, much further away. And because the universe is so big, I would be very surprised if we were the only civilization around. The universe is huge. As a rough rule of thumb, there's 10 to the power 11, that's 100,000 million stars in the galaxy, and 100,000 million galaxies in the universe. And not every star has planets, but a lot of stars have planets we're now discovering. We're finding lots of other stars in our galaxy have planets. If you look up at the night sky on a good night, you see lots of stars, and you should say to yourself, there are as many planets up there as there are stars. And surely some of these zillions of planets will have evolved life as well. Whether we can make contact, whether we can detect them, is another big, big question. It very much depends how far away they are. But the universe is huge, so I think there probably have been, will be, is life elsewhere.
And of course, lots of questions about the end of it all. You know, how the university might end. Dear me, that's a Freudian slip. How the universe might end. We could talk about that other one another day. But what would you say to questions around what the end might be like? Is the end imminent? People are getting quite apocalyptic on the questions, actually.
Yes. I don't know if it's to do with being in a pandemic or something. Probably
maybe.
Not, always these questions. I think ultimately stars will run out of fuel. Stars will go black. Galaxies will gradually go black. But meanwhile, everything is expanding. There's expansion still left over from the Big Bang. Everything is moving further apart, flying apart. There's a big black hole at the center of our galaxy. There's probably a black hole at the center of most, if not every, galaxy. Those black holes will continue to thrive as long as there's stuff they can gobble, but the black holes themselves, like the galaxies, are moving further apart. So as far as I understand, as far as I can see, the future is black.
Right, okay. That's a very cheerful, cheerful response there. Yes. There's a question about what the furthest star is that you've discovered. The furthest away.
I'm not sure I know the answer to that. When stars explode, when big stars explode at the end of their life, we can see them in other galaxies. Not very far away, but in other galaxies. So it's way beyond our own galaxy, but I don't think I can give you it in miles.
No, okay. There's an interesting question about how stars and planets get their names, which is quite interesting, isn't it? Because they have some wonderful names, and who decides, and how is that done? Have you had one named after you?
There is an international body, the International Astronomical Union, who agrees names. You can make suggestions to it of names, but it has the responsibility of agreeing the names of things, not just stars and galaxies, but of categories of stars, categories of galaxies as well, categories of planets, categories of asteroids, and so on. So the International Astronomical Union does all that.
So some questions around your own personal interests, and somebody's just posted a question about whether you read science fiction yourself, and whether you do you read science fiction with a professional eye at all, or is it something you just don't watch because you don't read or watch because it's just an impossible thing for you to cope with?
I don't
read it, so.
No, it's not because it's impossible to cope with, but because it's too like work. And I want
Yes.
something different when I'm not working.
Yes. And also, you probably know more than the authors as well. You know, you're probably spotting all the errors and mistakes that they make. Yes. You've had a long and distinguished career in astrophysics, and it's often thought of as a very male domain. How has that felt for you working as a woman in that environment?
It's felt like working in a male domain. Surprise, surprise. And particularly when I was younger, young women weren't seen as scientists. So it was quite difficult younger. Now I command a certain amount of respect, and that's better. And there are many more women now.
Yes.
But through most of my career, I've either been the only woman or the most senior woman wherever I've been working.
Yeah, I think that's a really interesting point, and it's certainly one that reflects, the university sector as well in terms of representation and but things getting better and things changing. And I'm aware from my own career of many young women coming into astrophysics, and hoping that they're still in there and that they haven't left, and that they've had good role models as well, which is so important. I'm often asked about what advice I would give to younger women starting out their career. Are there particular things you would offer as advice to young women starting in your field?
If it's something that really you enjoy, that grips you, go for it. It may not be 100% smooth, there may be setbacks, but if you're clear that's what you want to do, that will give you the strength to push through the blacker bits, the difficult bits, and ultimately come out the other side. I certainly find astronomy, astrophysics, hugely exciting. It's booming. It's going to continue to boom for several more generations, clearly, because of the equipment that's being built right now. So there's going to continue to be lots of exciting and, I'm sure, amazing results coming in. I think it's going to be huge fun as a subject. And it's gradually linking up with other bits of physics as well. gradually getting more information about particles in the universe. I've really been talking about light and the family of light. So it's linking with other bits of physics as well. What's dark matter? What's dark energy? Are there neutrinos emitted? What are the cosmic rays? Etc., etc. Lots of exciting new areas on the astrophysics-physics interface as well.
Yes, and a really good place for women to build a career. And I often say when I'm asked the question, keep a good network of support around you. Mentoring is such an important aspect of your academic career as well, isn't it? And I'm sure you've had good mentors and poor mentors in your life, as I have too. You've not had any? Oh, never a mentor.
I'm too old.
Yeah, I wouldn't say that. There's interest in what you're doing at the moment, Dame Jocelyn, in terms of your own research. Could you tell us a little bit about what you're doing at the moment?
Well, I'm no longer research active myself, but I'm trying to keep in touch with developments in part in the pulsar field, neutron stars. But I've also, because pulsars pulse, there is a time dimension, they're time variable, and I have also been following what other things are time variable, how they change with time. And we're discovering more and more things that change with time because we've got better equipment. It used to be that to see a distant object, you had to stare for hours and hours and hours. And for instance, the Hubble Deep Field, it was 143 hours of staring. And if anything changed its brightness in that 143 hours, the change was just averaged out. Now, with new equipment, we can study with much shorter time resolution, and we're discovering that a lot of objects flare and die away, or dim and brighten again. So a lot of things aren't as steady as we thought they were. Sometimes there are very short, sharp bursts of things from who knows what, but we're seeing them. So there's a lot of excitement now in time domain astrophysics, and that's going to really boom in the near future.
And do you think that the current renewed interest in space exploration is going to have a significant impact on the work of astrophysicists and certainly bring about great interest in the country in the way things are happening? The Apollo mission had a big impact in the 60s, didn't it? I was just wondering whether this renewed interest will match that.
There's a very worrying development, which is the constellation satellites, hundreds of them, that are going to be put up to provide internet connectivity. And they're going to wreak absolute havoc in the night sky. It's really, really serious threat to astronomy, that one. How do you see stars if there's forever, satellites zooming across in front of you? Crazy. So that's really, really worrying. That is. We're getting better at putting up satellites for astronomical studies, which is great. Someday we will travel to Mars, I dare say. Not this year or next year, I reckon, but it's probably coming.
You think in our lifetime we will see that?
Well, maybe not in mine, but probably in yours.
Well, I'm just thinking, there are so many things I've often thought, will we get equality in my lifetime? Will we get social inclusion in my lifetime? Will we get to Mars in my lifetime? Well, we are on Mars, but will we get people there? Yes, it's interesting to see how the speed of change and knowledge, opens up so many opportunities, and yet we still have so much to do. And we still have so much to do back on Earth as well, in lots of ways. This is a question that you might think is not to be answered, but and excuse me for answering it, but it is a question that lots of people think about, and it's about the intersectionality of one's own personal beliefs and faith with some of these scientific aspects and one's own scientific career. How have you faced some of those challenges in your career, in squaring, as it were, your own faith with your scientific life?
Well, I belong to the Quakers, the Religious Society of Friends, and they don't require you to believe something, anything. Well, they don't tell you what to believe. That's what I'm trying to say. And they say, work it out for yourself. And I have managed to work out something that seems to work okay for me. If I belong to one of the more regular Christian churches, there might be issues, I accept. But with the freedom that we have amongst Quakers, that's okay. I can do it. I do suspect there is a God. What I mean by God, I'm not going to attempt to explain, but don't assume it necessarily means exactly what other people mean. So I do think there is some sort of God. I think it's a God that says to us, you've got a life, get on with it, live it to the best that you can, but you're not told what to do. And that's something that suits me very well, which is probably that's what I believe. So you work out how to lead, for me, a moral life, and you do the best you can, which of course is always far from perfect.
Yes, that's a very, very deep answer, and certainly a very good advert for the Quaker faith, I should say, but also that sense of being able to hold things that aren't perfect, things don't fit, but being able to hold contradictions in that way in one's mind and heart, I think, is what you're saying, really, isn't it? That you won't get the answers one way through faith or one way through science, but being able to hold that tension and understand that tension is part of understanding that whole thing, isn't it? Because it is a thing that troubles a lot of people, and it goes to questions about the origins of the universe and what happened before the Big Bang and all these things and who set it all going. And we want more and more answers, don't we now? More and more satisfying answers with evidence and solidity, when actually sometimes things are unknowable to a large degree.
And untidy.
And exactly untidy, without steps and neat evidence. Yes. But it's certainly a question that a lot of people are kind of very concerned about. Somebody's 16-year-old daughter has just been watching and saying, if only they could learn this sort of thing at school. So clearly we have a wide age in our audience today, but I think some teachers tomorrow will be getting students saying they came to this tonight and they really want to know more about things, and that will be challenging for their teachers, won't it? So there's an interesting, again, a slightly whimsical question about whether there's a planet you would like to visit.
I'm not personally terribly keen on space travel. There's quite a lot of the Earth still like to visit, and whether I'm going to get there, I don't know. But I'm not personally grabbed by the thought of going to the moon or going to Mars or anything like that. And a number of the planets, frankly, wouldn't be very nice to visit. Mercury's too hot, and the outer ones are far too cold.
Yes. I think it's space travel. Perhaps we'll put that to one side for a moment about why anyone would want to do that. But I think whether there are areas of the universe that you've grown fond of in your time as an astrophysicist, because you've done so much work in those areas and you feel you know them in a very distant way.
There are one or two objects in the universe that I have battled to understand throughout my career. made some progress, but not, not finally solved. So there are interesting things in the universe, but not healthy to visit any of them. They often emit X-rays and gamma rays, which will be just lethal for our bodies. So you can only study them from a safe distance.
And just going back to those 1967 days, and the discovery. What was that like for you? You must have been asked this lots and lots of times, but people are very interested to hear how that felt being a postgraduate student and having that opportunity and doing that piece of work.
It was certainly a very exciting time. It turned up a number of surprises. My thesis advisor made very clear that my job was to get my thesis done on the original topic, that these new stars, the pulsars, couldn't be the thrust of the thesis. So I was sort of living a double life, continuing to work towards a thesis and also helping with studying these crazy, amazing new things, the pulsars. It was a very exciting time. It was a very great privilege to be involved. It was also a difficult time as a young woman, in part because I got engaged to be married between discovering numbers 2 and 3. I found the first 4, and wore the engagement ring to the lab, which was a big mistake, but I was very proud of that ring. And at that time, married women didn't work. It implied that the husband could not earn enough if the wife worked, and that was shameful. So wearing the engagement ring was not a bright idea, I now realise. It was also difficult around the publicity, at the time of the publicity around the discovery. There would be journalists and photographers, and the photographers saw young women as page 3 sex objects. And so I would be asked to undo some of my buttons for the photograph. And the journalists would ask, was I taller than Princess Margaret or not quite so tall? And what were my bust, waist and hip measurements, please? It was very, very sexist. And I would have loved to have been very rude to them, but I'm a graduate student who's yet to finish her thesis and get her degree. I can't afford to offend or fall out with senior members of the laboratory who seemed to think this was all perfectly normal. So I had to kind of grin and bear it, or be as pleasantly as obstructive as I could be, but pleasantly.
But it must have been, I mean, you must look back on that time, apart from the sexism, which we absolutely abhor, but it must have been wonderfully exciting for you and your family to be involved in that development and to have, your name associated with it throughout your career. And looking back at that time, the 60s anyway, the place to be in the 60s, but for that excitement to have happened in your life is a wonderful, must be a wonderful treasured memory for you.
Yes, I mean, it clearly has affected everything I've got to do afterwards. It's had a huge effect. I reckoned it happened because of imposter syndrome.
Tell us about that.
You'll know from my accent that I'm not Southern English. I had before then been in Northern Ireland, Yorkshire, Scotland, and turn up, rather to my surprise, in Cambridge to do a PhD, a research degree. And I find there are very, very few women there. There are lots of young men who seem incredibly confident in their own abilities, confident in their right to be in Cambridge. And I'm a bit isolated because there are so few women. And I'm more than overawed by the apparent academic brilliance of the place. And I become convinced that they've made a mistake admitting me, that they're going to discover their mistake before too long, and they'd throw me out, and I'd be sent away. And my policy, and I would recommend this to anybody who has doubts about their ability to, hold down a place at university. My policy was to work as hard as I could, do the best I could, so that when they threw me out, I wouldn't have a guilty conscience. I'd know I'd done my best, and it just wasn't good enough for Cambridge. So we now know this as classic imposter syndrome. We didn't identify, know about imposter syndrome at that time. There are now, incidentally, a lot more women in Oxford and Cambridge. It was particularly low at that time. And there are more women in science as well, so it's not as isolated. But whenever I find myself somewhere where I wonder, can I cope with this job? Can I hold down this job? I remember my ploy when I was a graduate student. Work your hardest, do your best. You can't do better than that. If it's not good enough, okay, it's not good enough. But actually, it probably is not only good enough, but really good. And you'll thrive.
Yes. Yeah. And I think today one hopes that there are more sources of support for women who find themselves in those situations that you had, and certainly more awareness and knowledge. But I think for you that must have been a very difficult environment in which to be working, particularly when you were being so successful, and not always acknowledged for that success. We're getting to the end now, so I'm going to let you go shortly. But just a question about the scholarship scheme, the wonderful scheme that you set up, and how that's with your prize money. Could you tell us a little about how that's going and what impact it's having now?
Yeah, I donated the money to the Institute of Physics to set up research studentships for people from underrepresented groups in physics. And that means women and ethnic minorities. It also specifically includes refugees, because I'm aware that it's often the intelligent people who've got out fastest and turned up on our shores as refugees. And the Institute of Physics, bless them, agreed to take on the money. They were doing quite a lot of work on diversity in physics anyway, and this fitted well with it. They've had one complete round. They awarded 4 studentships, 4 PhD studentships, all of them actually to women. It so happens, it doesn't have to be, but they were. 2 of them were women who had fairly recently come to this country to get a better life. One is from a very financially poor background, educationally not a wonderful background. She got, I believe, a D in her A-level physics, went on to do an undergraduate degree and did brilliantly, and is now doing a PhD, and I'm sure will do brilliantly at that. And the 4th woman is one who's recently had a baby and needs extra financial help in order to arrange childminding while she continues with her degree. There'll be another round fairly soon. They're saying they hope to be able to award 8 or 9 scholarships starting this coming October. Institute of Physics is adding some of its own income to the income from my money. And so I hope that gradually physics departments will become more diverse than they are already. I do believe that diversity is a strength. It's often more creative than having lots of people who look alike and think alike.
Mm. And are you able to engage with those that have received your awards? Do they get access to you as well as the money?
I've had Zoom meetings with them.
Oh, lovely! I'm sure that's such a benefit to them. Wonderful. Mm. Okay, well, Dame Jocelyn, may I just thank you for a wonderful late afternoon session with you on behalf of everybody on the call. And I think you heard that we had over 470 people who were interested in joining us. So I hope they're all out there and that they have enjoyed it as much as I have. You are inspiring. You're wonderfully engaging. I envy those young people who are able to work with you through your scholarship scheme. Would that I could start all over again myself and take on a different area of interest in my career. It would certainly be something in this field. And I know that we will meet again soon, and I hope in person, because we're very pleased that you've accepted to one of our honorary degrees and honorary doctorate of science. So our graduation ceremonies at the moment are online, but they, we hope, will soon be in the real world. And I very much look forward to welcoming you to one of our ceremonies to make that award, which is so justified in recognising your career and your contribution. So thank you enormously. I know that there will be hand claps around the country now, thanking you very much for this session. And thank you to everybody who has sent in questions. Some of them a bit cheeky, I think, but there we go. There's always a few, aren't there? I'd also like to thank First Sight Media for your expertise in putting this on for us. Thank you very much. And also the university's comms and events team who've worked behind the scenes to make all this happen, and I know have supported you, Dame Jocelyn, in preparing for this as well. So thanks to everybody for your interest. I would normally say have a safe journey home, but all you have to do is hop into the kitchen now and open the wine. So have a lovely evening, everybody. Thank you all very much. Dame Jocelyn, thank you very much indeed.
Thank you. Thank you very much.